Hey everyone, this is Karthik Chilkapati, and today we are going to be looking at two very fundamental concepts to dynamics, rectilinear motion and 3D particle motion. We're also going to see how this relates to aerospace engineering. So first, let's look at rectilinear motion. This type of motion is dealt in a 1D format, so we are only dealing with things in a straight line, meaning we only have scalar values. So in rectilinear motion, our way of measuring motion is done through three ways. One, position, we have r of t. Speed, which is v of t, and is also equal to the first derivative of position. And then we have acceleration, which is a of t, and it is the first derivative of velocity or the second derivative of position. And these are all scalar values because we are dealing with things only 1D. So you can always convert between position, speed, and acceleration through differentiation and integration. For example, if you want to find speed, you would just differentiate your position vector. And if you want to find acceleration, you would take the derivative of speed or the double derivative of position. Likewise, if you want to integrate, you would basically if you wanted to find speed, you would integrate acceleration, or if you wanted to find position, you would integrate speed, or you would integrate acceleration twice. Over here, we just have a general graph of what this can look like when we visualize it. So since each of these are the derivatives of the previous one, we can see that the velocity graph over here is the derivative of the position versus time graph, and our acceleration is the derivative of the velocity graph. That's just to put it into a visual spectacle of what that looks like. So moving on to 3D particle motion, right now we are going obviously in a three-dimensional format. And instead of scalars, we start using vectors with three components because it's in 3D. So things are not moving in a straight line. They could be moving left, right, up, down, forward, backward, and all. So like rectilinear motion, 3D particle motion also has equations for position, velocity, and acceleration, but it obviously looks a little bit different because we're dealing with three-dimensional movement. So r of t, and the arrow of the r is basically saying that it's a vector. We have an x of t, y of t, and z of t in the I, j, and k frame, which is also known as our Cartesian frame. So with differentiation, again, we are able to find velocity and acceleration equations. It basically works the same way. So here we have our velocity vector, and we can see that it is the first derivative of the position vector. So our x, y, and z are all differentiated ones to get a velocity vector presented. Same thing with acceleration, we basically take the first derivative of velocity, or we take the second derivative of our position vector, and we get x double dot t, y double dot t, z double dot t in the ijk reference frame. Once again, if we just want to like switch between any of these values, we would take the derivative, or we would basically integrate if we want to go from acceleration to velocity, velocity to position, or acceleration to position. So sometimes we can't go through this movement through integration to switch from acceleration to velocity or velocity to position because as we saw in our previous slide, we saw that all of our values were in terms of t. But that might not always be the case because sometimes, for example, acceleration can be in terms of velocity, position, and time. So this would leave us eventually with a differential equation to which we would need to solve in order to find our solution that we are looking for. So over here at the bottom, we basically see the basic structure of what a differential equation would look like. For example, our acceleration over here is in terms of velocity, position, and time. We basically have the initial values for velocity and position, but sometimes differential equations are really hard to solve, so we need to use software such as MATLAB or any other online calculator to basically help us find the solution that we are looking for. So how does this all relate to aerospace engineering? So when aircraft and spacecraft travel, they most obviously travel in a 3D plane. There's not a one-dimensional straight line that anything goes through because we live in a 3D world. So knowing the way that these objects behave while they're in motion can help many aerospace engineers analyze the movement of bodies and predict what can happen as a rocket or any other spacecraft or aircraft travels through air. So this can further help with analyzing airplane motion such as pitch, yaw, and roll, which are three very important movements relating to aircraft. And these have to do with angular velocity. And in order to understand angular velocity, you need to know the basic 3D motion that many objects obviously on Earth go through. Over here, I included an image to help better show why this is important, because we can see that our pitch axis, roll axis, and yaw axis are basically our IJK, XYZ, whatever frame you want to call it. But those axes are basically our Cartesian reference frame that we're looking at. So in order to understand pitch, yaw, and roll, we need to know that these axes exist, and we need to know how the plane acts when just moving through these axes. And that is it. Thank you. Now you all know about what 1D and 3D motion are and how they are important to aerospace engineering. Thank you.